to start with is pick our element that we want to balance. So what element do we want to start balancing?
AL.
Why'd you pick aluminum?
Because it was the first one.
First one on the list. Fantastic. That's actually a really good idea. The other option you could do is it's the first one on the list and it's not hydrogen or oxygen. Okay, so we could start with aluminum. How many aluminums on the left? Two on the right. Okay, so I heard a 3. Let's take a look at that 3. Why are you saying the 3? Because you see that 3, presumably, right? That purple 3? That purple 3 applies to what is directly in front of it. What is directly in front of it? The parentheses are what's directly in front of it. So anything within those parentheses is now multiplied by 3. Is the aluminum within that? No. So that 3 does not apply to the aluminum. Could say, well, there's another 3. True, that other 3 applies to only what's directly in front of it. What is directly in front of that 3? The oxygen, which is also not aluminum. Okay, which means, how many aluminums do we have on the right? 1. Is 1 equal to 2? I was hoping a faster response came out of that one. That's okay. No? How do I make them equal to each other?
Put a 2 in front of the right AL.
I'll put a 2 as a coefficient in front. Okay? Now I have 2 aluminums. Okay? Very common for students to go through and be like, okay, well, the 1's no longer right, so I'm going to erase it and write 2. I would argue that that is a bad procedure to do, because what you have done is erased your work. When looking at homework or checking your work, you want to be able to see the work. If you've erased your work, you don't know. So what I would argue you should do is that. Okay? Not a big deal. It's just a notational thing to kind of simplify and allow you to see that work. What should we balance now?
The NO3.
Okay, NO3 is not an element. We're going to address that a little bit later. So we've got a suggestion for barium. Okay, why'd you pick barium? Also not oxygen. Okay, so we could go with that. How many bariums on the left? 1. Barium's on the right. 1, right? So barium's balanced. What do we balance next? Okay. So I'm hearing a lot of nitrates, sulfates, SO4s. Actually, I think I heard SO3, but I'm going to pretend I misheard that was an NO3. Okay. I easily could have misheard that. What we talked about for our balancing rules was to balance each element. Okay, so I know where you want to go. I'm with you, but let's follow the rules as we elaborated on them first. Okay, so let's go through and look at the sulfur. How many sulfurs on the left?
1. Oh, no.
Okay, there is 1 in sulfate, but I have that 3. That 3 applies to whatever's in the parentheses. So there are 3 sulfurs on the left. How about on the right?
1.
There is only 1. Okay? How do I make the 1 equal to a 3? I need to put a 3 as a coefficient, the number out front, in front of the right-hand side. Everybody see that? Yeah. Okay. What's your question, Dominic? Wouldn't that change my other elements? Yes. I don't care at this point. We're just doing a pass-through and we're seeing what happens. Okay, but you're absolutely right. It would. What should I balance now? Whoops, sorry. Check our work. That now is a 3, right? Okay, what should I balance now? Oxygen. Never mind. We should jump to the nitrogen. We should save the oxygen for last. Okay, how many nitrogens do we have on the left? 2. You're right. Sorry.
It's okay. It's not like you spilled confetti all over yourself.
Fair enough. The lecture is young. How many nitrogens do we have on the right?
6.
Now you're wrong. Okay. Let's clean that out a little bit and let's take a look. Okay. So I did hear 3 nitrogens on the right. Okay? Probably because you saw the 3 there with the parentheses, and that multiplies through. So that would be 3 nitrogens. Except, what does this coefficient apply to? Everything afterwards, which means 6 nitrogens. Is nitrogen balanced? What can we do? What do you got, Faye?
I just have a question.
Yes.
So that means that the 3 on the inside of the parentheses, it doesn't matter?
What is the 3 on the inside of the parentheses referring to? It's only referring to what's directly in front of it. What is directly in front of it is the oxygen. Okay, and yes, that's challenging. So I need 6 nitrogens on the left. How can I make this 2 nitrogens into 6? I will change the coefficient to 3 what nitrates? Barium nitrates. It's okay. Okay. And now we have 6 nitrogens, right? So now what do we do? Oxygen. We still haven't balanced out. Okay, so now we could go through and check oxygen. How many oxygens on the left? Oh boy, exactly right. That's why we saved to do oxygen at the very, very end. Okay? So if we go through and look at this, we had 4, but there's 3 of those, which means 12. There's 3, but there's 2 of those, but there's 3 of those.
This was a science class, not a math class.
Okay, everybody track that?
Yeah.
And not what he said, what I did. Okay, so how many oxygens?
30.
We now have 30, right?
Do you breathe easier with 30 oxygen?
I'm just going to pretend I knew what that meant. Okay, let's take a look at the product side. How many oxygens do we have? We have 3, but we have 3 of those 3, which means, but I have 2 of those 9, so I get 18. Oxygens from the other side. I get 4, but I've got 3 of those 4, so I've got 12. 12 and 18 is 30. Yeah? Okay, so let's slow that down because I saw a couple people looking at me like, what the hell are you doing with all those arrows? Okay. Let's pick one that's a little bit easier. Let's take a look at the barium sulfate. Okay? And you'll see why I want to pick the easier one because the other ones are going to suck to draw. Okay? If I was to draw this out, I have barium, sulfur, 1, 2, 3, 4 oxygens. Yes?
Yes.
How many of those do I have?
3.
How many oxygens have now been written down?
12.
Okay? So when we're looking at those arrows, that's effectively what we're doing. We're drawing out each of those things. If you're having a hard time seeing that, that's fine. Okay? You're not going to like the suggestion, but then you get to draw them all out like this. Okay? So let's do it with one more. Let's take a look at the aluminum nitrate, and let's break that one down. Whoops. Go away, hydrogen or water. We have aluminum. Oh. And I have 1. No.
No.
But I have 3 of those. Okay. But then I have 2 of those sets. Okay. How many oxygens are now in that? 18. Okay? So what we went through and did was 3 times 3, right? Because it was 3 times 3 times 2 because we replicated it again. Everybody see that? Okay. So if you have a hard time seeing those pieces, that's fine. I completely understand that. You should really draw it out to prove that you can see those oxygens and that you understand what we went through and did. Does that make sense? When we total our oxygens, we then say 18 plus the 12 we had over here. That gets the 30. We would still technically have to do that long process over on the other side. Does that make sense? Okay. So now that we've balanced out our oxygen, now what should we do? We would check our work by effectively deleting everything and resetting this up. Okay? I don't want to delete everything because I just spent so much time doing that, and I don't want to write it all out again. Okay? But we could go through and check that. I'm going to delete the bottom part. No. I appreciate that you want to make me write more, but let's be a little bit more productive in our writing. That's our job. Okay, so let's go the bottom direction now for our work. How many aluminums? 2 and 2. How many bariums? 3 and 3, but we said we had 1. But as we went through, we continued to change. Okay? So if you rewind back, you might actually hear in the recording me being like, do you have a problem, Dominic? Because he wanted to do something. He wanted to double back after we did the sulfur to look at the barium. Okay? Don't. Just continue through the process. Because what might very well end up happening? You work it out. You'll fix the problem. Okay? If you start doubling back at different times, you're going to be constantly cycling through in multiple different stages. Do a full cycle, then do a full cycle, then do a full cycle. Does that make sense?
Trust the process.
Okay? You kind of have to trust the process. Okay? What was next? Way to be tricky. Let's throw in nitrogen. Nitrogen wasn't next on our list. We went to sulfur, but let's check our nitrogen. How many nitrogens do we have on the left?
18.
God, I keep doing it again. For the 118, thank you, because that's what I was about to say too. Remember this 3 applies to only the oxygen. There's actually only 2 nitrogens there. With the 3 gets us 6. Okay, I did the 18-2 in my head. Okay, we go to the right-hand side. How many nitrogens do we have? 6. Then we can do sulfur. And what's our sulfur? 3 and 3. Our oxygen, 30 and 30. We've now gone through a second time where we didn't change any numbers, which means we're arguably done. Okay, but we could go back and check it again. Okay, we are actually going to go back and check this one again, but we're going to check it in a slightly different fashion. Okay, we're going to check it by running a different method, a method that a couple other people had been shouting out that we try and do, and I said we shouldn't do it right away. Okay, so let's remember the conclusions that we came out of this. Our coefficients were 1, 3, 2, and 3. Whoops. Yeah? Everybody understand that notation? So if we asked for the sum of the coefficients, you would tell me 11? 9? Because we've got 4 and 5. The sum of our coefficients would be 9. Okay? Make sense? Okay. So, is there another way we could do this? Because remember, we did a lot of work for that. So let's try it again. We're going to start this time with aluminum. I didn't say the difference showed up right away. We look to the left, what do we got? 2. To the right, we've got 1. How do we fix it? Right? And here's where I'll go ahead and change it. I'm going to balance SO4. Okay? You might say, well, why can you do that? That's not balancing an element. SO4 is sulfate. It's a complex ion. Did the complex ion sulfate change in the course of this reaction?
Yes.
No. This is aluminum sulfate. This is barium sulfate. I can group all of those elements as a single unit and just balance it as that unit, sulfate. So how many sulfates are on the left? 3. Sulfates on the right? 1. That's not balanced. How do we fix it? Make it a 3. Okay. I can now move to the next one, barium. How many bariums on the left? On the right? 3. That doesn't balance. What do I need? Okay. So our barium's down balanced, and now I'll balance nitrate as its own unit. How many on the left?
6.
Okay, so we got a couple different answers there. Remember, nitrate is that parentheses. I have the 2 applying to it, and then I have the 3. I get 6 nitrates. Okay. On the right-hand side, how many do I have? 6. Is my nitrate balanced? Yeah. So now what could I do? Go back and check all my work. Take a look at the numbers that we pulled out of this. This other method, we get 1, 3, 2, 3. It's an exact match as if we had done it atomic. Does that make sense? Okay. So we can go through and balance things as whole units as long as they stay whole units across the equation. Okay. Does that make sense?
Yeah.
Okay. What do we got?
So if we were given like a quiz question or a homework question, would you rather have us do the individual elements or the ones
So,
just how it was?
good question towards kind of homework or exams, okay, which is really kind of 2 questions. On an exam, I'm probably not going to ask you to show your work, okay? With a question like this, it's kind of borderline, you being able to do it in your head. Some people might be able to pull that off. I'm now asking you to do busy work behind it. Most of the show your work questions aren't just busy work. You really need to show your work, because if you don't show your work, you're doing it wrong. Okay? So I would argue it doesn't fit as a show your work for an exam question. It's going to show up as multiple choice. Okay? When it comes to homework, a homework is a whole nother beast. What's the point of the homework? To show that you know how to do it. Providing the answer doesn't show that you know how to do it. That just shows that you know how to flip open the book to the answer key and write down the answer. Okay? So what I want to see in the homework is some form of work. Okay? And again, it doesn't have to be right, but it has to be showing how that you would come through it. If you're having a hard time balancing, you're like, I don't know what to show for this because I don't know how to balance it. What could be something that you could write down for the work?
Definitions.
Okay? Help, I don't know, aren't going to really qualify. What do you mean just try?
Show your thought process.
What thought process?
At least the elements.
Definitions? It's balancing chemical equations, right? Did we talk about it? Did I give you, say, a list of steps that maybe you should follow? Maybe what you could show as your work is, I don't know how to do this, but here's the steps that I looked up on how to do it. This step, I don't understand. You're now pointing to a specific aspect that you're having problems with. Now I can help you. If you just say, I don't know, I'm like, well, which do you not know? Do you not understand that A needs to stay with L because that's the symbol for aluminum? Okay. That's a really big issue. That's way back in Unit 1. If I start going through and explaining to you what are the individual steps, that's meaningless to you because you aren't at that level yet. Does that make sense? So you have to provide some context both for you and for me if you're going to try and get any help from me. Does that make sense? Okay? Questions? So, homework, you show a lot. Okay? Error on the side of being like, this is dumb, I shouldn't have to write this. On the exam, you show enough that you get it right. Okay? Or that at least you think you get it right. Does that make sense?
Yep.
Okay. Can I clear it? Faye, you kind of had a hand. You're good? Okay. So let's look at one more. So we'll start, okay, we could start with this and say hydrogen. Is hydrogen okay to balance in this case? Starting with hydrogen. Why is it okay?
There's only one on each side.
Hydrogen only shows up once on both sides of the equation. It's okay. Okay, we could start with the hydrogen. How many hydrogens on the left? 2. Where's my, there it is. 2. How many hydrogens on the right? 2. So the hydrogen's balanced. Okay. Oh, Mike just said I can balance by complex ions, and I know enough about nomenclature that I know that carbonate is a complex ion. I'm going to balance carbonates across this equation. Did carbonate stay in existence? No, which means I cannot balance carbonate because it's not on both sides of the equation. It has to maintain the same on both sides of the equation. Right? So I would have to balance this instead as carbon and oxygen. How many carbons? 1 and 1 oxygens. 3 and... This is why oxygen and sometimes hydrogen can become challenging, because it shows up in multiple places. There's 2 oxygens there, there's 1 there. 2 plus 1 gets me my 3. Which means the equation is balanced. The sum of the coefficients is 3. Guess what answer choice could show up? 0. You'd be like, oh, there's no coefficients. There's an implied 1. There has to be an implied 1. Because if it was implied to be a 0, it wouldn't be written down. Okay? Kind of make sense? We good? Yes?
So the coefficient, the number that's after like CO and it's 2, that only goes to the oxygen. It doesn't go to...
True, and that's not a coefficient.
What is that called?
I'm going to kind of delay here and be like, this is the coefficient. And then this subscript is the... what was it called?
Subscript.
Okay, that's all I had for. I was hoping you guys had something fancier. All I've got is a subscript. Okay, what is the subscript reference? Okay, and number is a bit vague there. The amount of thing to left. I'm hearing a lot of people say element.
Yeah.
Okay? That 3 is a subscript. It's not referring to an element. It's referring to the thing, the parenthetical, which is a lot more.
So
Yes.
the subscript 3, would we apply that to the O and the S separately? Or
That subscript 3 applies to the parentheses. What is in the parentheses? S, 1, 2, 3, 4. So that 3 applies to whatever is in there. So that means I have to do that 3 times, which would become S.
oh, so there's only 3 S's and
There'd be 3 S's and 12 O's.
okay, so technically we don't write a 1, so it'd just be a 1 after
And it's always going to be an implied 1, because if it was implied as a 0, why would we have written the symbol? Okay?
So in this case, the sum of all the coefficients would be 3.
In this case, the sum of the coefficients is 3. Okay? What is the coefficient? Sorry, vague question. The number here is 1. In general, the coefficient would be and we're hearing a quantity. Let's try and keep our phrasing similar. The amount of thing to the right
Would that be 2?
up to an operator. And actually, kind of borderline on operator, because we could just do a separation. So let's call it, I always screw this up, ER? Okay, up to some kind of spacing. Okay, because before we put in the plus, what are we going to put in? A space. Okay, if we put a 2 in front of this water, that 2 would apply to everything that came after it up to an operator. Well, there's no operator, so it just applies to everything. No, it's up to that space. Does that make sense?
So what's the coefficient again for the purple?
The coefficient for the which one?
The purple writing?
The coefficient is the amount of the thing to the right of the coefficient up to a spacing. So in this case, that number has to be a 1 because, again, if we implied it as a 0, it wouldn't make sense because 0 times anything would be 0. So why am I writing it if it is deleted?
And when you answer that, do you want us to write 1 or?
So when you answer it, you can write whatever, well, if it's 1, you can write 1 or nothing. Okay. Arguably, placing the 1 is a good thing to do because now you know to add it. Okay. It is not a requirement, and to the best of my knowledge, no instructor will ever take points away from you for doing that.
It doesn't follow under like the laws of.
I don't think there's a nomenclature type rule on it. Yeah, I don't think there's a laziness law.
Would you ever have to add the total subscripts?
Adding the total subscripts doesn't make sense.
Yeah.
Okay? And even adding the coefficients, the only reason we would do that is for what? Exam question. There's no reason why I would just add all those things together because they're referencing different substances on different parts of an equation. The only reason why I do that is to then ask, did you know how to balance the equation without having to draw out 5 different possible balanced things with all the coefficients and numbers and stuff. Okay? So it simplifies the test question by saying provide the sum of the coefficients. Okay? So it's merely a test question aspect. Nope. Okay. We good? Cool. Okay. Classifying chemical reactions. Okay. It doesn't look like anybody prints out the slides, but just so you know, we're about to do just a giant slide shuffle. I apologize. Okay. But you do? Someone said I do? Damn it. Okay. Classifying chemical reactions. These are our chemical reactions. Officially, we have one more that I always forget to add back to the slide, which is a combustion reaction. That's ION. The combustion reaction is CXHY plus O2 gives you, not that, CO2 plus H2O. Okay, in all of these cases, we're not balancing it in this form. All we're trying to provide is the general format for the equation so that when you see a specific equation, you can now classify it according to these categories. Okay, why? Well, we can do different things according to those categories. Certain genres of chemical reactions have different requirements. For instance, a combination reaction, you are not required to predict. You're also not required to predict a decomposition reaction. Why? Most of those reactions, or a lot of those reactions, have some very complex chemistry going into them that you wouldn't be able to predict easily. So we'd have to give you a whole lot more of a knowledge base behind chemistry to allow you to do those. Right? We already have enough stuff to cover, so we just say, don't worry about predicting them, recognize them, and balance them. Okay? When you look at the textbook will have you predict combination and decompositions, usually because they're providing you some extra context. What's the extra context, or where is the extra context found? In the chapter. If you read the chapter, it says this is the general format for a combination reaction. So the questions in the book are now asking you to use that context to answer the question. Okay? On an exam, you're not expected to do that. Okay? What do you notice that's different about the combination and decompositions versus the single, double, and neutralization reactions? There's a color change. Okay? That color change is because we're adding more information for the single and double and neutralization reactions. Okay? That's bringing in some information about cations and anions. We're actually getting more specific in our general format. Okay? You need to be able to look at any equation and quickly classify it according to those rule sets. Okay? Particularly if you're only given the reactants. You need to be able to classify it. Okay? Why if you're only given the reactants? Because if you can look at the reactants and say that's a combination, what question do you know is not going to be asked? What are the products? Because you're not expected to predict the products. But if you can look at it and go, that's a double replacement, guess what question is coming down the pipe? What are the products? Okay? So you have to be able to classify these relatively quickly. And that's the point of these categorizations, is to help you do that. Okay? The combustion of all of these is arguably the easiest because it is the most narrow definition. Okay? This definition is really excessively narrow, but that's how we're using it in Chem 130. We take carbon with X. The hell is X? It's some subscript. It can be any whole number bonded to hydrogen with also some whole number. And I'm going to react that with oxygen. Anytime I do that, I can change X and Y as much as I want. Every single time, what do I end with? CO2 and water. Okay? It's always going to produce that. Okay? So it's a very narrow definition because it works really, really, really well. Okay? There are other cases that are also combustion that kind of expand outside that a little bit. Don't stress about qualifying those. Okay? And here's where we get to, of course, apologize, because now that we've got these general ideas of what all these things are, let's just massively shift gears. Okay, fine.
While we're pausing, this is a really great moment to note that this is a type of communication with socially agreed upon norms and conventions, otherwise known as a what?
Genre.
That's what.
Yeah. These are specific writing genres in chemistry.
For those of you watching at home, Mike said that already.
Cool. That's how you know we've been hanging out.
Wait, are you recording this or listen to it at home?
It's good to have it reinforced.
You can listen to it at home, yeah. Every single, so we're now like week 7, end of week 7. Every single lecture has been recorded and posted to Canvas.
Wait, really?
Every single lecture.
We've said that, like Mike said that, or I've said it like 6 times. I think I remember telling you guys that I'm subscribed to his channel.
All the stuff on the first day just goes.
Oh, I know it's on the YouTube.
Yeah.
Wait, I'm so confused.
Let's go back to math. Let's go back. It's okay. Mathematic simplifications. If I asked you to write that out in your notes and do it in your calculator, might you get upset a little bit? Why? It's okay. You're saying it's too much work because I'm asking you to do it twice, yeah? What are you saying? Why? Okay. We have a way to simplify that. We could write that as 4 to the 6. Okay. This is the use of exponents. Okay. Some people are familiar with this, some aren't. Okay. If we go to our calculator, your calculator has multiple functions that can do this. Sometimes it's called exp for exponent. Sometimes it's x to the y. Sometimes it's y to the x. What does that mean? It depends on how you're entering it into the calculator. If it's x to the y, the number that you've entered is your x. If it's y to the x, the number you just entered was the exponent. Okay, so you have to make sure you understand how your calculator functions with that. Okay? The exponent shortens the amount of work that we have to go through and do. It makes life easier. Okay? So there's some common exponents that show up. We see squared and cubed a lot. Why? Calculate the area of a square. Length times width, which would be 2 dimensions. And so our squared is squared. It's referring to the area of a square. It's to the second exponent because you just multiplied twice. Cubed, length times width times height, you multiplied 3 times. Okay? That's where those terms are ultimately coming from, the areas of those shapes. Okay? Powers of 10. Okay? Dang it, I meant to fix that. Okay? Which is ultimately going to be looking for scientific notation. When we look at our powers of 10, they're repeated multiplications of 10. So if we see 10 to the 6th, that means 10 6 times. We could go through and do our zeros as well. Okay? That's the point of those powers of 10, is to take a number that's really, really big or really, really, really small and scale it into a system that's a little bit easier to comprehend. Okay? Sort of. By making it easier to comprehend, we actually made it harder to comprehend. Okay? And you might say, well, that's a load of crap. Okay? Look at your national debt. Okay? People go, oh, 19 trillion. It's probably not even 19 trillion. That's how much I pay attention to it. What are we, 20-something? 22? 22 trillion. Well, that's not that bad. I got a 20 in my pocket. How bad can it be? And then you actually write out all the zeros, and you're like, holy mother of God. Okay? By saying 20 trillion, we've shortened the amount of zeros that append afterwards so that it's easier for us to write and look at, but it also removes a lot of that meaning about how seriously massive that number is. Okay? So just be aware of that. We do a lot of things with scientific notation to kind of get the numbers into a more manageable state. Okay? Those numbers being 1 through 10. Okay? That kind of sucks with a number like 20 trillion. That makes it more difficult because we have to go to 20. But okay, we like to get our numbers into that 1 through 10 range. So we will make adjustments, 37, 55. We will make adjustments to scale those numbers accordingly. Okay? That's the point of our powers of 10. Okay? With that, we can go through and do scientific notation. So scientific notation takes these massive numbers or these really small numbers and tries to remove a bunch of the zeros so that it's easier to write. Okay? So the number up here becomes 4.063 times 10 to the... Okay, and this is exactly what I was hoping to hear. I heard a -8. Okay, and you would say, well, negative because I shifted the decimal to the right or the left. That method is inherently flawed because depending on which way you're going to scientific notation or out of scientific notation, the direction you shift the decimal point changes. Okay? So you can be like, oh, if I go, well, this way, this time it's this way, or this way, that time. Yeah, it's just a stupid method. Okay? Look at the size of the number. Is that a big number or a small number? It's big, which means the power of 10 needs to be positive. How about the next one down? 1.16 times 10 to the... Now that's a small number. I got you. It'll become negative. Okay? What about the size of the number that I'm using as my exponent? There's an implied decimal point for that first number. I shifted it 1, 2, 3, 4, 5, 6, 7, 8 places to get to scientific notation. That's the 8. How about the small number?
Go past the first one.
1, 2, 3, 4, 5, 6, 7. It's not past the first decimal point moving. That's the number that we're putting in there. It's how many places you moved it. Right? If the number is big, make it positive. If the number is small, make it negative. Yes?
How do you know where to put the decimal point?
This is your paycheck. How much did I pay you?
1,000 something.
How much did I pay you?
10,000.
How much did I pay you? Okay. Where's the decimal point? Wasn't specified in any of that, and yet what did you do? You already knew where it was. There's an implied decimal point with almost all of our large numbers. And no, it's not a stupid question. You've got it. You just have to recognize that you do know that information. Sometimes information you'd think is encoded or not, and you have to make sure that you know how to decode that information. You already have it.
I think she was asking more why you made it 4.063 instead of 40.06.
Yeah, that's not.
Okay. Where do I place that decimal point? So let's go through and take a look at this. So 40.63 times 10 to the 7th. I didn't shift it quite as far, right? Do these numbers have the same value?
Yeah.
Yes, they both end at the same place. Are they both scientific notation? No, and in this case, they both have the same number of sig figs.
It's just.
The top one is not scientific notation. Why? Because somebody said scientific notation has your first significant digit located where? In the ones place. And if we look at the number 40.63, our first significant digit, that 4, is placed where? In the tens place. It is therefore not scientific notation.
Okay, I guess that.
Okay? Which is completely arbitrary and a bit nonsense as far as I'm concerned, but that's the rule. Okay?
So can we
Scientific,
can we
social.
write another one down?
You can take your social norms and... I know.
Can you write another one down for us?
What's that?
Can you write one more down for us?
So we can go through and do another one here, and we'll make it a little bit more challenging. I do see your hand. Give me a second. Give me a number. How many zeros? Okay. Let's turn this into scientific notation.
7.6921 times 10 to the.
So first digit, significant digit, goes into the ones place. Whoops. So it becomes 7.6921 times 10 to the... Now how far did I shift? There's an implied decimal here. We went 1, 2, 3, 4, 5, 6 places. Was that number large or small? Large, which means it needs to be positive. Okay.
You're only going to have like a number 0 through 9 and then a decimal point. And then a something.
You will only have the number 1 through 9 in the ones place because the 0, you can't start 0 as a significant digit.
Okay.
That goes all the way back to our sig fig rules.
So 1 to 9 and then a decimal point.
And then a decimal point, yes. Okay. Then all of our significant digits afterwards. Okay. Are those last two zeros significant? No, why not?
Is there a decimal point there?
There was only an implied decimal point. Because there's only an implied decimal point, those zeros are not significant. To make them significant, what would I need? A decimal point or another significant digit to the right. Okay? Yeah? So why not? Because we're seeing some people that are like, I totally get this. Let's break you. There's your 4 zeros. I want that number reported to 3 significant digits. Do whatever you can do.
Because it'd be 760 decimal place times 10 to the third. Right?
You want that 3 significant?
3 significant digits. I want 3 significant
You
digits.
said make it significant without, you didn't specify in what form we should put it in. That also leads to like the question I had before. Because like,
Oh, I did forget. Come back to you, sorry.
shouldn't it be like any place greater than 1 to do it instead of a big number versus a little number? So if it's less than 1, then it's a negative.
Oh, yes, yeah. Well, less than 1 is a small number.
Well, yeah, but 1 can also be a small number. Depending on how you put it.
It's all your frame of reference. Yeah, I can understand that. So let's go ahead and take a look at this. So we said 3 significant digits, which means if we underlined our significant digits, we would get 7, 6, and 0. The most common answer I get from this question would be this. It is now 3 significant digits. And I go, fantastic. That was now your paycheck, and I only decided to give you that. Are you going to object?
Yeah.
Okay. You changed the value. When we change sig figs, we cannot change the value. The meaning behind the number must stay constant. Okay. So how can we maintain that value? Okay. One suggestion was saying times 10 to the third. If we go through and look at this, again, we have an implied decimal point. How far did we shift it? 1, 2, 3. So we would get 760 times 10 to the third. Okay? Where we're going to run into some issues with that is that 3 sig figs.
No, that's full place mark. They have to put a decimal.
I would have to include a decimal. But now I've got a decimal next to a mathematical operator. Doesn't that look kind of weird?
So when you put another 0 as a placement marker?
Add another 0. Now how many sig figs?
4.
That's now 4. Damn it!
Never mind.
So I can't add another 0 there. So again, stupid stuff underneath the text. So having a times next to the decimal point just looks weird. Okay? We could throw spaces in. I can understand that use, but we have another way that we can clarify that. That's kind of at the top of the slide. 7.60 times 1, 2, 3, 4, 5. For those of you that could do that in your head, jerks. Right? And our number becomes 7.60 times 10 to the 5th. Scientific notation allows us to take these crazy weird numbers and scale them down a little bit. It also allows us to maintain the meaning of significant zeros that we would otherwise have lost. Right? And where some people kind of flip out with this one is go, but you're losing information with this. Okay? No, you're assuming that I'm counting out to the ones place. But when I count out 760,000, am I really going to count out all the ones?
No.
No. What I'll probably do is count accurate to the thousands. I'll just group them based off of thousands. This is $1,000, $1,000, $1,000, until I get 760 of them. I may still have some left over, but in the grand scheme of things, that leftover stuff, I might be like, it's not that big a deal. I won't worry about it. As you go, I'm always going to care about that. Has anybody just left the change after you've paid for something and been like, I don't need that? I definitely do that because I don't want the freaking change in my pocket. Okay? Right? Depending on where you're at in a system, You may decide that that information was super important and you might record it. In most of our daily lives, we really care about that extra change and we hold on to it. Okay? I definitely went through a time where I was holding on to every single cent that came back. Okay? Now I get irritated, or really I started getting irritated when I had to bike everywhere. When I was biking everywhere, I didn't want to carry around 5 pounds of freaking change with me. And it was just irritating. So I wouldn't take it. Okay? Because I would just lose it. Okay? And that's true. I ended up sacrificing my ability to buy like water, in which case that sucked. Yes?
So let's say you wanted it to 4 sig figs, what would the answer be?
Okay, let's switch it up. 4 sig figs. How do I fix it? I probably shouldn't have erased all that. So 7.600. So there's my 4 sig figs times 10 to the... It is still fifth. The decimal point didn't move. All I've done is add another 0. That other 0 is now significant because I have a decimal point. To be significant, all I need is a significant digit to the left. I want 5 sig figs. What do? I add another 0. Every 0 I add now will always be significant.
So if you add another 0 to that equation right there, is it still 10 to the 5th?
So let's be careful with that. If you add another 0, is it still 10 to the 5th? And what you said was I add another 0 to that. What is that? If I add a 10 to the 0 or another 0 here, is it still 10 to the 5th?
Oh, no.
Absolutely.
Then it changes to 1.
If I add another 0 here, now is that going to potentially change things? Okay. If we go through and evaluate that, now where's your implied decimal point? After the green one, now it jumps up to 10 to the 6th. So your that becomes very, very questionable because depending on where you're placing the 0, we're going to get different meanings. Okay? And because you're shaking your head at me, let's walk through that. Okay? Let's take a look first at the green or the purple and green one. You're like, but that changes it. No, it doesn't. Shift the decimal 5 times. We want to go out of scientific notation. It's a positive value, which means my number should be what? Big or small? Big, which means my decimal point needs to move that direction. So I need to move how many times? 1, 2, 3, and actually 4, 5, 7, 6, 0, 0, 0, 0. Adding that 0 didn't change anything. Okay? Nothing about that was a problem. Where you might be having a problem, and now I got to clean a lot of that out.
This video is going to be fun to watch.
Especially
7, 6. How many zeros do we have? We have 4?
4.
I should have just erased the whole thing from the get-go. Okay? 7.6. 1, 2, 3, 4, 5, 6. 10 to the 5th. Decimal point.
And that turns into 760 pounds.
Is the meaning, is the value, numerical value still the same as this?
Yes.
So if we
Yes.
keep adding zeros to the end of that, it would still be the same thing as...
So same thing. Again, we're getting a little weird with our vagueness on those terms, and that's where we have to be careful. Does it have the same value? And this is where we're going to run into some issues with how we qualify our numbers. So let's go through and write out what this number in green means. Positive value, so I need to shift the decimal so it's getting larger. So 1, 2, 3, 4, 5. My number becomes 760000. Decimal point 0, 0. Is the numerical value the same?
Yes.
Is the meaning the same?
No.
No. Why is the meaning different between the red number and the blue number?
Specify the change.
The blue number has specified the exact change. The red number has not. Okay? That red number belongs to the set that is at a maximum, technically actually, somewhere in between there. And this gets fun with making our observations. You might be like, that's a huge range. That is. That range comes from sig figs. According to how that red number is written, how many sig figs do we have?
2.
We only have 2, which means that 6 is a guess. Okay, so actually, technically, it gets worse than that. Those could really go up to 9 or 0. It could belong anywhere in that range. That, as a measurement, is not very precise. Okay? If you won the lottery, do you want some precision? Yeah. 1 billion, that's probably a bit large for the lottery, isn't it? That's 450 million is a large number. But if you got 450,900,000, do you want that extra 900,000?
Yeah.
That's a pretty significant chunk of change that you would also like to have. So when we think about our everyday experience is nitpicking the detail out of every last dime, quarter, cent, everything we do. Why? Because at the scale that we work with, we want all of that. Now let's switch up your life. Okay? You won the lottery again, but you're a billionaire. Is that 900,000 quite a big deal?
Yes.
Yeah.
You might not care as much. Why?
No, I don't think so.
The amount of that scale of that loss isn't a major issue. Okay? So depending on where you're at on that economic scale, you're going to evaluate that monetary loss differently. We talked about people being like, I'm going to grab every last cent back. Right? There's billionaires that are paying $20 for a hot dog. Okay? Would you pay $20 for a hot dog? No, why not? That's stupid to pay $20 for a hot dog. It's just a freaking hot dog. Why does the millionaire or billionaire pay $20 for it? Because they have the money. They don't care about that scale. Okay? That's the exact same issue that happens for us when we move into science. Except what are we doing in science? We're going exceptionally large and exceptionally small, which means we have to care. Because if we don't care, what ends up happening is we kill somebody.
You lose your money.
Okay? Okay? So we want to be a little bit more careful with those sig figs. That's why those sig figs become important. That's why it's important that we have notational systems that keep track of that information. Okay? And we have to have an agreed upon fashion on which to monitor it. Because if we don't come to an agreed system, what happens when you try and collaborate with another company? It doesn't work. So we have to have an agreed upon system. Okay? How many of you like group work? That's not a lot of hands. Okay? Why not? Why do the rest of you are like, I don't know about group work? It's that one lazy person. Okay? It's that one person that doesn't have the exact same expectations as you. What did scientists do to prevent that issue? Here's all the freaking expectations. You either match them or you don't contribute.
It's my little brother.
Okay? Science has built a system that forces the collaboration and sets a minimum standard. When we look at group work in academia or in our classes, that minimum standard isn't as easily defined. Science, we have it defined very strictly. And if you don't meet that standard, you don't get to contribute, period. Okay? So, That's our scientific notation. We can look at sig figs. We already actually did this example, so we don't need to stress about that. Okay. How do we make our numbers really big or really small? Because we went through and did those numbers. I already forgot our numbers. 21 times 10 to the 5th. That means I would have to write this 10 to the 5th a whole bunch of times, and that could get tedious. Okay? So scientists also created a system to be inherently lazy, to say, I don't want to write times 10 to the 5th. I want to write it as something else. Of course I picked 5th. Let's try 6th. Okay? I don't want to write times 10 to the 6th because that's too many hand gestures. Instead, I'm going to say 10 to the 6th is capital M. I've now simplified the amount of writing. And you're like, dude, that's nonsense. What was our national debt again? 22 trillion. It's the exact same system. It's not 22, 3, 4, 6, 9, 2, 3, numbers until we've achieved trillion. Okay? We shortened it and we appended a random word to simplify our writing or our counting of it. Okay? There are multiple ways that we can use this information and manipulate it. So the first thing we're going to do is the simplest way because it helps achieve some of the scientific notation aspect.
So wait, if someone says they got 1K, means they got 1,000. But if someone says they got 1 G, 1,000 G's, would that be 1,000?
So, and this is where you're going to have to be careful with your sociocultural norms on what does each of those G's refer to. Okay? So you have to be a little bit more careful to acknowledge what system you're in. Okay? Some of those systems, like I've got 1K, translates very easily because kilo is a super common reference. Okay? 1G. Okay? That's a little bit different. Why? Because we have a different sociocultural norm on what that 1G is referencing. Okay? If you can start referencing to the amount of G's you've got and you're referencing gigas, that's pretty cool. Okay? So, in red, we've got 3 of them highlighted. Why would we highlight those 3? Those are incredibly common. They are so common that it makes a lot of sense to memorize. Okay? I've been very selective about what I tell you to memorize. I want you to memorize the things that you use so often. Because if I didn't have you memorize them, guess what happens the amount of time it takes you to complete any task? It goes through the roof. You spend too much time trying to find that information. So some information you have to hold on hand. Kilo, centi, milli are prefixes you should memorize. Okay? How should you memorize them? Okay? You should memorize what the prefix is, kilo. You should memorize that it's represented as a single letter, as a lowercase k. And you should memorize that it means 10 to the 3rd. Centi, C, and it means 10 to the minus 2. Milli, 10 to the minus 3. The centi and milli, we will encounter issues with those. Okay? And for that matter, for the kilo, when we talk about how we've dealt with our past experiences with these unit systems. Okay? And we'll encounter that when we really push into conversions. Okay? We aren't doing a whole lot of conversions today, so I don't want to push into that yet. Okay? So let's take a look at how we could use scientific notation to manipulate this. I have 1,200 meters. What is the scientific notation for that? What did 10 to the 3rd mean? What did 10 to the 3rd mean? Yes, we could talk about shifting decimal points. That was scientific notation. We're not on scientific notation as a slide. We're on the prefix slide. So 10 to the 3rd means kilo, which means that measurement is now 1.2 kilometers. Okay. What about the next one? 1.2. Why'd you make it -2?
Because it's smaller.
That number is a relatively small number and really smaller than 1. We're ignoring negative numbers. Okay? What is 10 to the -2? That meant centi. So that measurement is now 1.2
Centiseconds?
centiseconds. How many of you have heard of centiseconds? It doesn't mean it doesn't exist. Okay? It's there. Okay? Do you guys want to try the last two, or do you think you got it?
I think yes. That would be 1.2 milliliters, right? Wait a minute. It'd be 1.2 and then that would be 1.2 milligram. Oh, that's right.
Kilo was 10 to the +3. Milli is 10 to the -3. Don't just associate 10 and 3 to mean kilo. Positive versus minus makes a big difference.
It is a test question.
And it is a test question.
It tends to be a recurring test.
Okay? So we now have a way to represent those. Why would we do that? That's a whole lot of zeros. Are those zeros significant? No, they're placeholders. I don't want to have to write a bunch of just placeholders. By changing the unit system, I now don't have to include the placeholders, and I maintain the value. Okay? That's pretty sweet. And you all thought I didn't make any jokes. A couple people heard it. It's fine.
What?
Yes.
I'm kind of confused on why you had to change like the N to KM and the G to.
On why I had to change?
Yeah.
It's not a had to, it's a choice.
Oh, so if
I am choosing that writing 1200M takes too much effort for my wrist, and instead I'm going to write 1.2 km.
That's the same amount of effort.
Okay? For those people being like, well, that's the same amount of effort, make the number bigger. Make the number smaller. Okay? We're picking relatively simple values. Okay? It's ultimately a way to shift systems so that we don't have to do all of that extra work when it becomes extra work. Okay? Why do I know it should be km and not millim or centim? What did I say 10 to the third was? K. That's why it becomes K. So converting it into scientific notation allows me to now make that alphabetic system translation. Okay? What we want to write down, if we look at the bottom part, why am I shifting to milligrams? I only want to put down the useful information, the meaningful information to the assignment. Okay? So when doing project 1, what did you decide was useful to include in that? Was there information that you were like, oh, I don't need to write about this? Or did you write about all aspects of your research?
Most of all of them.
Most of all of it? Some, not all of it? Okay. You should have made very careful choices about what to include. Those choices or behind that should have reflected something about the assignment, like who are you writing for? Okay. You're writing for your classmates. So the information you included was to help your classmates. You're writing to a chemistry teacher. So does it make sense to talk about physics? Probably not. That information isn't going to be relevant to the audience that that assignment is targeted for. We want to write the information that is only necessary for that task. Make sense?
Again, that's a rhetorical consideration in science, in writing about science, or because you're being
So,
intentional.
all we're establishing is how do we make that transition. One of those transitions is to put it into scientific notation and recognize that we can represent 10 to the minus 2 by something else. Just like I can represent gold by something else. Yeah, what can I represent gold by? AU. Okay. Why did we write AU instead of gold? It's shorter. We're lazy. You guys go, oh, this is not that difficult. 2 zeros versus K. Gold versus AU is 2 letters. But what about beryllium? How many of you can spell beryllium right now? Yeah, okay? So we come up with a different system, okay, to shift that.
I wrote beryllium down. I got that stuff.
Okay? We're creating a system that can be applied and scaled. What we talk about initially are the easier examples. Why? Why do we talk about the easier examples? Because they're easier for you to process and interpret. If we jump in right at the most difficult examples, what happens? You all get lost. Okay? So, let's take this a little bit further. There's our fractional notations. In English, there are 1,000 meters in 1 kilometer. Mathematically, that means 1 kilometer equals 1 km equals 1,000 meters, right? Multiplication. What do you mean multiplication? I don't see any multiplication.
Well, it would be implied between kilos and meters.
What if I divide both sides by 1 kilometer?
You have 1 meter equals...
I try again. I don't get 1 meter. Okay, I'll run with that. I get 1,000 meters over 1 kilometer. What does that equal? I always find this fascinating how everybody gets stumped by that.
1,000 meters per 1 kilometer, 1, right?
Does that help? What does it equal?
1.
It's not 1 kilometer. It equals 1. That's it. It just equals 1. And you'd be like, well, why is that useful? I want to be able to convert now 3 kilometers into meters.
3,000 meters.
Okay? 3,000 meters. What did you do? You multiplied by 1,000, right? Okay, so let's go through and do that. Times 1,000. Is that equation true?
No.
No, that's not valid.
Oh, that's still 3,000.
That's 3,000 kilometers. That's not 3,000 meters. What'd you do? I don't want kilometers as a unit. I had to divide out the kilometers. How many kilometers did I divide out? 1. I also want what unit as an answer? Meters. Where did this come from? So what you did in your head is exactly what this conversion section is about. Everybody goes, oh, I don't need to show any work because I know how to do that in my head. Because they're easy conversions. The point of this unit is not to be like, yeah, I can multiply by 1,000. I know you can multiply by 1,000. Okay? What I don't know is that you know a unit system that allows you to track your work. Because what's going to happen in the next unit is I'm going to change those units so you can't just multiply by 1,000 because you don't have a meaning to associate it with. Because you won't know what a skittle fart is.
What is a skill fart?
stick around.
I don't
Right?
think I want to now.
As soon as we change those units into something you're not familiar with, your entire process for solving crumbles. What you need to focus on is what is the process for solving your conversions. That's the important part. And if you can't identify a process, you will fail the rest of the semester. I cannot stress that enough. If you cannot identify a process for how to do a conversion, you will fail the rest of the semester. Okay? Work on identifying that process. Didn't get anywhere near as far as I wanted to. I would keep lecturing, but I think we'd get a mini revolt.